So next we can have the wave function in form of ground state. So we know that we have represented the ground state as K0. So A acting on K0 vanishes, it becomes 0. So in the cosine basis, I can write A is 1 by square root of 2m is cos omega m omega x plus ip. So plus I p can be as minus I h cross dot by x, and h0 I can write as u0. So A acting on h0 can be written as 1 by square root of 2m h cross omega m omega x. I into I become minus, and there is always already minus, so it become plus h cross dou by dou x u0 of x is equal to 0. So that shows that dou u0 by dou x, we can take all other things to the right side, and that would be 1 by that would be m omega minus m omega by h cross minus m omega by h cross into u0 of x. Okay, now this and there is one x also, minus m omega x by h cross u0. That's correct. Then dou u0 of x by u0 of x becomes minus m omega by h cross x into dx. Integrate it. So if you integrate, it will become log u0 of x would be minus m omega by h cross x square by 2 plus some integration constant, and u0 of x can be less some constant k0 e raised to minus m omega by h cross x square by 2, or a0 e raised to minus alpha square x square. So that is u0 of x, and now this u0 of x is the same form that we have got in the Schrodinger picture, and we can find a0 from the normalization condition, that is minus infinity to plus infinity u0 of x square dx is 1 integral minus infinity to plus infinity mod a0 square, and this square becomes e raised to minus alpha square x square dx not equal to 1. So this is the integration of a Gaussian function. Integration of Gaussian function is well known. Answer is minus into plus infinity e raised to minus ax square dx. This is root pi by 8. Okay, now it is minus alpha square x square integration. So therefore this will be root pi by alpha, and hence the result will be mod a0 square into root pi by alpha equal to 1, and hence mod a0 would be alpha root alpha by pi raised to 1 by 4. And what is alpha? I think alpha we have found here. So alpha square is m omega by h cross. So alpha is nothing but square root of m omega by h cross. So root alpha becomes m omega by h cross all raised to 1 by 4. So that is your a0. So hence what would be your u0 of x? So u0 of x would be m omega by h cross all raised to 1 by 4 e raised to minus m omega by h cross by 2. So that is your ground state wave function. So this is the way to find the ground state wave function. Okay, so we have started with this is a acting on 0 is 0, and I represented this basis. Okay, and that helped me to find the functional form of u0 of x. Now from this I can find the functional form of the first excited state. So how to find the first excited state? The kid 1 is given by a dagger acting on 0. So since I have already found out my u0 of x, by acting a dagger on u0 of x, I can get u1. So u1 of x simply equal to a dagger acting on u0 of x. But again, there should be some proportionality constants, the normalization constant. So the normalization constant I will put it as a1. And what is a dagger? A dagger is 1 by square root of 2m x cross omega m omega x minus ip acting on u0 of x. Okay. Now in question basis, the operator x just put as x, and operator p just put as minus a h cos operator x. Now by knowing u0 of x, we can find the form of u1 of x, and I think no need of a1, so we can find a1 because a dagger acting on u0 is simply become u1. There is no need to put any normalization constant anything. Okay, so this is enough. So this you can do it yourself. I think this will also be kept as a homework assignment to you. Okay, so I am just stopping it here. Okay, so the rest of the steps you can do, that is how to find u1 of x and compare this u1 of x with the u1 of x that we already got in the Schrodinger picture. Okay, so we have got u0 of x, and this u0 of x is exactly same as that what we have found in the Schrodinger picture. So similarly, you can show that the u1 of x that we found here would be same as that we have found in the Schrodinger picture. Okay, so that the steps, the remaining steps, you can do it as a homework to you. Okay, so that will be written assignment to you. Okay, now the last thing is I will find what is the expression for the a and a dagger, how to represent a and a dagger, etc. in matrix form, in the operator form, or that is called the matrix representation of operators. So this is the last topic we have, the matrix representation of operators, how to represent an operator in the matrix form. Okay, so this discussion we already discussed earlier when we were discussing the first module, the mathematical formulation of quantum mechanics. Okay, so you can record linear representation depending upon the basis vector. So first we have to choose the basis vector. Okay, so what I am going to do is I am going to represent the operator like an annihilation operator, the creation operator, or number operator, etc. in get n basis. So get n is the energy eigenstate or the eigenstate of number operator, and this is the number operator or the Hamiltonian operator is the Hermitian operator. So and therefore its eigenstate, the set of eigenstate can be chosen as a basis. So this n can be chosen as a basis, and what are the possible value of n? There can be get 0, get 1, get 2, etc. And what is the dimension of these vectors? These dimension can go up to infinity because n can run from 0, 1, 2 up to infinity. So this is an infinite dimensional vector. So you have to represent k0 as infinite dimensional vector. So k0 I'll represent as 1, 0, 0, etc. It will go up to infinity, and there will be infinite zeros down. Okay, so the get n is a vector and infinite dimension Hilbert space. So I will represent get 1. So get 0 and get 1 should be orthogonal to each other because these are the eigenvalue corresponding to different eigenvalue. So for any Hermitian operator, the vectors corresponding to different eigenvalues should be orthogonal. So one and the get 0 and get 1 must be orthogonal. So there cannot be 1 here. So the first term I can put as 0, and next can be 1, then other things can be put 0. So then how will you represent get 2? So get 2 can be represented as 0, 0, get 1, 0, 0. So these will be the simple way to represent the get vectors in a matrix form. So I am representing the get vectors as a column vector So then obviously the bra vectors are represented as a row vector. So that is the usual convention. Okay, so there is no need to write the vectors in this form, the ket vectors and column vectors, all this. That is depending upon you. So the most preferred choice is the ket vectors are represented by the column vectors and bra vectors represented by the row vectors. Okay. And we have discussed all these things in the mathematical formulation. That is why I am not putting the much time on this. I am directly go how to represent these operators. Okay. Now in order to represent any operator as a matrix. So suppose you have an operator A and you want to represent this operator as a matrix. What I will do is I should know what is the action of the operator on the basis. Suppose A is the operator you want to represent. A is the operator you want to represent in the phi n basis. That is their basis vectors phi 1, phi 2, phi 3, etc. Then we can represent the operator A in the matrix form once you know what is the action of this operator on the basis vectors. That is the action of A acting on phi 1. The first basis vector can be represent the first column, and the action of A acting on phi 2 can be second column. Action of A acting on phi 3 can be third column, etc. The action of A acting on phi n can be nth column. So this is the way, this is the easiest thing you can remember. This is the symbol way to represent an operator in the matrix form. Okay. So then in order to represent the annihilation operator in the basis n, you should know what is the action of A acting on ket 0, what is the action of A acting on ket 1, what is the action acting on ket 2, etc. Okay, so you can recall the action of A acting on n is simply root n minus 1. So therefore A acting on ket 0 is simply 0, and A acting on ket 1 is ket 0, A acting on ket 2 is 2 times ket 1, etc. So root 2 times ket 1, because A acting on ket n is root n minus 1. Then how will I represent A? So A, according to this definition, so A acting on ket 0, that will be a first column. A acting on ket 1, second column. A acting on ket 2, third column, etc. And since it is an infinite dimensional Hilbert space, A is operating in infinite dimensional Hilbert space, so it will have infinite terms, infinite columns. Okay. So after represent the first column, the A acting on ket 0 is simply 0, so it is a 0 column vector, it is nothing. And A acting on ket 1, the A acting on ket 1 will be ket 0, so it is a ket 0 vector. So ket 0 vector is 1. The first column, the first element is 1, and all others are 0. And A acting on ket 2, A acting on ket 2 is root 2 times ket 1, and this is your ket 1, root 2 times ket 1 would be 0, root 2 0, etc. So can you guess what would be A acting on ket 3? So A acting on ket 3 would be root 3 times ket 2, so this will be 0 0, root 3, etc. The next would be 0 0 0, root 4, etc. So it will be infinite. So it will be infinite dimensional matrix. Okay, infinite dimensional square matrix. So this will extend up to infinity. So this is the matrix representation of operator A. Now how will you represent the matrix for operator A diagram? So again recall A diagram acting on n is root of n plus 1 to n plus 1. Okay, so the A diagram, the matrix form, A diagram acting on ket 0, A diagram acting on ket 1, A diagram acting on ket 2, etc. And what is A diagram acting on ket 0? That will give root 0 plus 1, that will be 1 into ket 1. So that will be ket 1, and ket 1 is 0, 1, 0, 0, etc. And it will go up to infinity. And a dagger acting on Ket 1, it will be root 2 times Ket 2. So that will be 0, 0, root 2, 0, etc. And the next would be a dagger 2, that will be root 3 times Ket 3. So this, the first row would be completely 0. Here the first column is completely 0. Here the first row is completely 0. And the next column will be 0, etc. So this is your a dagger operator and this is your a operator. And now we can find what would be the position operator, x operator. X is square root of x crossed by 2m omega a plus a dagger. So right now we have got a and a dagger, just add it and you will get x. The operator x can keep square root of x cross 2m omega common outside. So this entire column, that column, if you add, you will get 0, 1, 0, 0, etc. The second column, it become 1, 0, root 2, 1, 0, root 2, 0, etc. Then third is 0, root 2, 0, root 2, 0, root 2, 0, root 3, etc. Then okay, 1, 2, 3. Then fourth one 0, 0, 0, 0, root 4, 1, 2, 3, 4, 0, 0, 0, 0, root 3, 0, 0, root 3. Then I think that's correct. 1, 1, root 2, then root 2, root 3, then 0, 0, root 3, 0, 0, root 3, 0, root 4. So that's it. So this is the position in the matrix form, the position operator in the matrix form. Now similarly you can find the momentum operator and we can find the Hamiltonian operator. Now the Hamiltonian operator is very simple. So how to find the Hamiltonian? The Hamiltonian H acting on Ket n is simply n plus half. So H acting on 0. So H acting on 0 would give 0, Ket 0 with energy half h cross omega. So the Hamiltonian, the first is H acting on 0. H acting on Ket 0, that would give Ket 0, but energy would be half h cross omega. So that would be h cross omega by 2, 0, 0, etc. And the first exercise state for n equal to 1, Ket 1, it would be 3 by 2 h cross omega. And for, so this H acting on Ket 1, this is H acting on Ket 2, H acting on Ket 2 will give 0, 0, they will get Ket 2 itself, but the energy would be 5 by 2 h cross omega 0. So if you look at this expression, this Hamiltonian in the matrix form would be a diagonal matrix. It would be diagonal matrix, and diagonal elements would be its eigenvalues. Okay, so why it is so? Because the thing is, the Ket n that we are representing here, this Ket n is the eigenstate of the Hamiltonian operator. So if you represent an operator in the eigenbasis, it will be a diagonal matrix with the elements would be their eigenvalues. So that is the result that we already know and we have illustrated it. So in case of harmonic oscillator, if you choose the Ket n is the basis state, or the energy eigenstate as a basis state, then the representation of Hamiltonian in the matrix form would be a diagonal matrix, okay, in which the diagonal elements would be their eigenvalues. So first diagonal element is the eigenvalue corresponding to the ground state, the first excited state, second excited state, and so on. Okay, so similarly, if you put if you represent the number of operator n, what would be the result? Okay, so that would also be a diagonal matrix. Okay, so all non-diagonal elements would be 0, and only diagonal elements would be present. What would be the first element? That would be 1, because that would be 0. That is n acting on 0 would give 0. Okay, then next is 1, 2, 3, 4, etc. And those are the possible eigenvalues for the number operator 0, 1, 2, 3. There is a possible value of n acting on n, small n, n, for n can be 0, 1, 2, 3. Okay, so that's it. And with this, we have completed the discussion of the matrix representation of operators. So with this, we have completed the discussion of quantum dynamics. Okay, so in quantum dynamics, there are mainly 3 different pictures we have discussed: Schrodinger, Heisenberg, and interaction picture. And we had illustration of these pictures only for one particular system, that is for the quantum harmonic oscillator. And we have shown that for quantum harmonic oscillator, the result of both the pictures, that is the Schrodinger and Heisenberg picture, are same. And that is remarkable because the Schrodinger and Heisenberg picture are based on entirely different philosophical footing and even different mathematical footing, but we are getting the same result. So one way it is remarkable, and another way we can call it as it is also a dilemma in quantum physics. So there is not a fixed approach for the quantum physics. You can do in different ways, but the results are same. And next class we have a small tutorial session. Thank you.